first thing I want you to realize, okay, I'm not going to ask you any questions about this, but we're going to be using circular motion to answer every single question just about, and so it's a good review of the circular motion equations. We want to talk about universal gravitation. The law of gravity, you may have heard it described. This is the equation that Isaac Newton came up with. So we've said that gravity is a force that exists between the Earth and masses on its surface. In fact, gravity is universal. It exists between any two masses in the universe. All objects with mass send out a gravitational field, almost like the invisible tentacles of an octopus, in all directions. And they tug on all other objects with mass. All of you are sending out a gravitational field. Not very big, but it's totally there. Example 2 says this: the diagram below shows masses big M and little m. You know what? Let's make it and moon. Okay? Earth has mass, so it's exerting a force of gravity on the moon. The moon has mass, so it's exerting a force of gravity on the Earth. Compare the gravity forces on each of the masses. A, the force exerted by the Earth is bigger. B, the force exerted by the moon is bigger. Or C, the forces are identical. Once again, we get to vote, Alec. Once again, how high you hold your hand up is how sure you are of the answer. So the Earth tugs on the moon tugs on the Earth. Which force is bigger, or are they the same? Who says, Mr. Dewick, obviously A is larger, because Earth is bigger, because Earth. 1, 2, 3. 3. Who says the moon is bigger? The moon exerts a bigger gravitational force. Who says the forces are identical? Why is C correct? Actually, there is an acceleration, but the acceleration changes their direction, not their speed. That's a good thought. Go to a different law. How about forces come in? Pairs. Ask your question, Elias.
Well, I thought the moon orbited around the Earth.
Earth also orbits around the moon slightly. The Earth has a slight wobble due to the moon. We call those tides. That's what gives us the tides. Now, the Earth has a big enough mass, F equals what? The acceleration that the Earth experiences due to the moon is not noticeable. We don't feel the Earth moving around or anything like that. But the force has to be identical. That's what Newton's third says. Forces come in pairs. But we're going to dive into it a bit more, okay? When Isaac Newton was looking at the law of gravity, he found that gravity between two different masses depended on three things. He noticed that the force increased as the first mass got bigger, which means in our equation, the first mass will be on the top. He noticed it increased as the second mass got bigger, which means in our equation, the second mass will be on the top. But he also noticed that gravity got smaller based on the square of the distance between the masses. Say what? Here's what he noticed. The force of gravity, and here's a new symbol, a little fish, is proportional to or depends on the mass of the first object, the mass of the second object, divided by the square distance between them. Because he noticed when the distance got bigger, the force got smaller, so the distance must be on the bottom. But he noticed it was a square relationship. Problem. The units for this would be kilograms squared per meter squared. Is that a Newton? No. So we need a conversion factor to turn this into an equation. In the same way as we multiply seconds by 60 to get minutes, or we multiply meters by second by 3.6 to get kilometers per hour, we're going to put a conversion factor right here to turn this into an equation. And the letter that we use for that conversion factor is capital G, big G for gravity. In fact, we call it the universal gravitational constant. So if I want to turn this into an equation, it's going to look like this. The force of gravity anywhere in the universe is big G m1 m2 over r squared. Unfortunately, that conversion factor is a bit yucky. It's not a nice 3.6 or a 60. It's on your formula sheet where all the data is. What is big G? Read it to me, Alec.
I'll try.
Yep.
6.67 times 10 to the negative 11.
And then the units to get it to be newtons end up being Newton meters squared per kilogram squared. That gives you something in newtons. Okay? By the way, big G is 0.000000000667. Gravity is a very weak force. It's by far the weakest of the four fundamental forces. You think it's big because it dominates your life because you live on a large mass, the Earth. But it's the weakest force by several billion. It's by far the weakest force. That's why you can lift stuff up. Okay? This is the law of gravity. Mass 1 times mass 2 divided by, I made it an R instead of a D because in a few seconds we're going to start moving in circles, but the distance between them. But to get an answer in newtons, you need to stick big G in. So just as a basic example, I have a 1 kilogram mass right here. If I had a second one here and I held them 1 meter apart, they are tugging on each other, technically, because they have mass. How big would the force of gravity be between two 1 kilogram masses separated by 1 meter? Well, the force of gravity is big G m1 m2 divided by r squared. So it's going to be, what was big G? 6.67 times 10 to the negative 11. Cole, put your calculator down. Cole, how big is mass 1 in kilograms? How big is mass 2? What's the distance between the masses? What's 1 squared? What's 6.67 times 10 to the negative 11 times 1 divided by 1 divided by 1? I hope you weren't typing that into your calculator. Some of your calculators, if you have constants on the back, will actually have this constant pre-programmed in. Okay? And it'll be called big G. There's a little shortcut you can do. But here's what I really want you to realize. So right now, you and the person that you're sitting next to are exerting a tiny force of gravity on each other, but it's negligible. We don't even include it in our calculations. Is that a hand up? Yeah, it adds more digits, more sig figs. What direction is the force of gravity? You ready? Toward the
Center.
Which means it's also a circular force. We're going to combine them in just a second. Although sometimes gravity can behave a little strangely. Put your pencil down, look up. That's why planets tend to get pulled into spheres. In fact, that's one of the official definitions of a planet now. A planet, to be a planet, has to satisfy 3 things, and one of the things it has to satisfy is it has to have had a strong enough gravity to have pulled itself into a sphere. That's why asteroids aren't planet, because they're all weird shaped. What's going on?
It's tilted.
Yeah, it's a tilted room. And clearly she's wedged into that couch and also wearing some pretty strong hairspray or something, because there's no hint that gravity is acting at a 45-degree angle when you look at her.
Have you been drinking?
No. Have it later.
Tea?
Yes, that'd be lovely, thank you. No, I'll get it. It's fine. Hello? Yes. Yes. Yes, this is he. Right. Certainly. That's the hospital. I'm wanted in surgery urgently. I must leave immediately.
So, normally gravity acts towards the center, and this brings us to the application for circular motion, orbits. Example 1 says, draw a force diagram for the mass little m, let's pretend it's a satellite, in orbit. What are the forces acting on it? Ooh, there is the obvious one. Which way would gravity be pointing?
Center.
And I'm not going to call it mg anymore, because now, since we're going universal gravitation, mg doesn't work because we're high enough that g is not 9.8. Instead, let's just call it fg, and we're going to use the universal gravitation equation to do rocket science. We're going in outer space now. Okay? An orbit is circular motion with gravity as an inwards force. In other words, if we were doing this full unit, this would be your trigger word. Anytime you saw the word orbit, you could say, gravity is what's pulling me in a circle. Example 2 says this, a 10,000 kilogram satellite is orbiting 20,000 kilometers above the Earth's surface. Write force equations and find the orbital speed. The first thing we're going to do is cross out 20,000 kilometers. How do I convert that to meters? $20,000 kilometers is 200 meters. 20,000 kilometers is 2 football fields. I don't think you divide by 1,000. Someone, anyone. How do I convert kilometers to meters? Times by 1,000, right? 1 kilometer is 1,000 meters. 2 kilometers is 2,000 meters. So I'm going to write it like this. 2 times 10 to the 7th, because there's a lot of zeros. And I'll put the meters there. And could you do me a favor? Underline the word above. Okay. A says write force equations. What path is this satellite tracing out? What's the force pulling it in a circle? Gravity is what's pulling me in a circle. Okay? For gravity, I'm going to use our new version, big G, and then in the original version, I gave you M1, M2, but often in rocket science, what we do is we use big M for the planet and little m for the satellite over r squared, and that equals m. And then look up, please, once you've written the little m after the equal sign. In my imagination, I'm seeing the AC there, but then I go, which version do they want me to use? What's B asking me to find? So I'm going to use the v squared over r. Oh! I noticed something kind of weird. One of the r's will cancel. So I'll cancel out the squared on the left and the r on the right, because I can move the r squared to the top and there'd be 2 on the top one. But what else?
How do you have that?
It turns out once a satellite is in orbit, its mass is irrelevant. All that matters is how fast and how high. So the space shuttle and a tiny satellite, they'll orbit at the same velocity, at the same height, regardless of their mass. What do we want to find? How would I get the little v by itself? Square root. Here it is. This is, sorry, let's do, this is part B now. So v orb is equal to big G, big M over r orb. That's the equation for orbital speed, and it comes out of circular motion. Couple of problems. This 2 times 10 to the 7th is not a radius. What word did I underline here? So this distance is 2 times 10 to the 7th. I need this distance from the center of the Earth. How can I figure out that distance and that distance? Shh. What? I'm going to have to add the Earth's radius. Okay, so you ready? Here's our numbers. We're going to have a big square root symbol. And unfortunately, the universe does not give us nice numbers. Because first of all, what was big G? More specific. What was big G? Yeah, you're right, Nicole. 6.67 times 10 to the negative 11. Big M is the mass of the Earth, also on your formula sheet. They didn't estimate it, they calculated it. Can you save that till the end of the lesson and I can show you? Okay? I'll save that to the end of the lesson and I will totally show you. I normally do it with you in this second gravitation unit, and I skip that because I'm cutting corners like crazy. And then the orbital radius is going to be 2 times 10 to the 7th plus the radius of the Earth. What's the radius of the Earth on your formula sheet? Okay. How the heck would I type this in? I think probably I would go type what's inside the square root first, unless you have one of those nice calculators, those lovely double, if you can do 2-level fractions, you can just type this in. For me, I would go like this, bracket on the top, 6.67, scientific notation, negative 11, times 5.98, scientific notation, 24, close bracket. divided by, open bracket, 2 scientific notation 7 plus 6.38 scientific notation 6, close off the bottom. And then I would go square root answer button. You should get 3,888 meters per second. Yep. It's not like this is rocket science or anything. Oh, it is rocket science. There you go. By the way, here's what that means. When we launch rockets, we're having to give them fuel for two things. We have to give them enough fuel to get this much potential energy off of the Earth and that much a half mv squared kinetic energy. When you see a rocket, 90% of that rocket is the fuel. Only 10% is the payload. Okay. Note that orbital speed is independent of the mass of an orbiting object. It depends only on orbital radius and central mass. In other words, V orb equals the square root of big G, big M over R orb. That's the equation we derived, and it comes out of, Calvin, gravity is what's pulling me in a circle. It's circular motion. Okay? I'm going to skip example 3, but we talked about this a little bit last year. Objects that are in orbit are in free fall. Now, how does that work? In an ingenious analysis of orbits, Isaac Newton, before we'd even invented hot air balloons, was imagining outer space and orbits. He said, imagine a big mountain on the Earth with a cannon. You could fire a cannonball, boom. If you added more gunpowder, you could fire a cannonball, boom. He said, it seems to me if I add enough gunpowder, I could fire a cannonball at just the right speed, boom. It's falling towards the Earth, but it never gets any closer. That, Nicole, is what an orbit is. Every object that we have, all the satellites, they are all falling towards the Earth. But we give them just the right sideways speed. What sideways speed? That one. So that although they're falling, they're always moving sideways, so they're constantly missing the Earth even though they're trying to fall towards it. All objects in orbit are in free fall. And that's why, Diego, they float, because they have objects up there, astronauts up there float. Because when you're in free fall, there's no normal force. There's gravity up there. In fact, you can calculate gravity. The gravitational field on the International Space Station is not 9.8, it's about 8.7. But they don't feel it because in the same way when I jumped out of an airplane, I jumped out of an airplane, I don't feel it because I'm in free fall. In the same way, remember the opening thought puzzle for those of you that were here? In free fall, this cork would not experience gravity at all. It will just float in one place. It won't experience buoyancy. So all of our satellites, every one of them, they're falling towards the Earth. They just never get any closer. The fact that an object is in orbit is in continuous free fall is interesting. First of all, it means they're always falling towards the Earth, even if they never get there. This explains why they seem to float around in the space shuttle or on the International Space Station. Both the passengers and the ship are all falling at the same rate, which means the ship can't exert a normal force on the astronauts. And so this is why I've been trying to tell you since last year what all of you think of as your weight, Justin, is the normal force pushing up. This means also that astronauts experience continuously, until they get used to it, the feeling of falling. It takes your stomach a day or two until you stop feeling nauseous. Example 4. In a cartoon, a character kicks a football the wrong way, backwards, but the football orbits the Earth and goes through the uprights in the other direction. At what speed was the football moving? What path is this football tracing out? What's pulling it in a circle? Gravity. Gravity is what's pulling it in a circle. But now that we're going orbital, we can't use little mg. We have to use the more complicated version of gravity, big G, big M, little m, over r squared. And that's going to equal m. Am I going to use the equation with the v in it or with the t in it? What does A want me to find? Oh, so v squared over r. Did they need to give me the mass of the football? Well, that's nice. And one of the r's cancels, not both of them. How would I get the v by itself? In fact, it's the equation that we derived about 2 minutes ago. V orb equals the square root of big G, big M over R. So let's crunch in the numbers. Let's see. We're going to get this. What was big G? 6 something, something, something. 6.67 times 10 to the negative 11. Big M was the mass of the Earth, 5 point something. And then, I guess if we're orbiting right near the Earth's surface, R will just be the radius of the Earth, which was 6.3 something. If you did want to orbit right near the Earth's surface, how fast would you need to travel? I don't know. Fine, figure it out. I'll give you a hint. It's going to be faster than 3,888 because the closer you are, the faster you have to move to stay in orbit. The further you are from the planet, because the gravitational field is weaker, you don't have to move so fast to stay in free fall. What'd you get, Nicole? 7,900 and... Yeah. Just under, I know it's just under 8 kilometers a second. I know it's always just under 8,000. So 7,910 meters per second. How long would that take? It's a good question. What does B want me to find? More specific in terms of circular motion, what does B want me to find? T. What did we just find in part A? Is there an equation for circles that has a V and a T in it? This part is on your test and fair review. There is an equation that has a V and a T in it for circular motion. Which one?
BC equals 2 pi r over t.
Braden, how would I get the T by itself? Where's the T right now? On the... Yeah. Wait a minute. I could multiply it to the top and divide the V down. T is going to be 2 pi r over V orb. So it's going to be 2 times pi times 6.38 times 10 to the 6th divided by, and just use your answer button there. How long would it take to orbit the Earth at the Earth's surface if you were doing orbital speed? I think this might even work out evenly with no decimals. I think. Could be wrong. Or maybe I'm totally wrong. I might be wrong. Calvin, what'd you get? 5,070. Anybody else? Yeah. How long is that, Kelvin? Could you divide that by 60? How many minutes?
84 minutes.
Yeah, you're going around the Earth every 84 minutes. I know the International Space Station, which is higher up, travels a bit slower. It goes around the Earth roughly every 96 minutes. Okay, which means they get roughly, I think, 10 sunrises and sunsets a day. Okay. Diego, can you read C to me, please? Part C.
Why is it not possible to orbit the Earth's surface in this manner?
And then what's the hint?
It is possible.
So why doesn't this work on Earth, but why would this work on the moon?
Is it radius on
No, had nothing to do with the radius. Good thought, though. No. No. Yeah. Doing this on the Earth, air resistance. Look how fast you're traveling, 8 kilometers a second. Air resistance would slow you down really, really fast. Is there air on the moon? And so probably if we do ever build, and I hope in your lifetime we get a permanent moon base, on the moon you could do satellites slightly higher than the highest mountain on the moon, and they're good. You basically orbit at the moon's surface. The other issue, of course, on the Earth is you'd have to dodge Mount Everest and things like that, but there's probably a sea level path. Oh, that's a good question. I wonder if there is a complete circumference on the Earth somewhere that is pure sea level and never goes over any land. Now I'm wondering, I got to go get a globe. There's one behind. I'm going to go look at that later. Anyways, hey, is there air in outer space? That's why satellites work so well, but we have to get them up and out of Earth's atmosphere, which requires more rocket fuel because we got to give them more potential energy. I think a couple more, we're done. Okay. Suppose we want a weather satellite to orbit the Earth every 300 minutes. So let's suppose you're you're SpaceX, and a company comes to you and they say, we want a weather satellite, we want to orbit the Earth every 300 minutes. The first thing you would say is, nice try. 300 minutes is what? Yeah. By the way, 300 minutes, I think, is every 5 hours. So you would actually probably have said, we'd like our satellite to cover the Earth every 5 hours. Okay, for the physics, we would convert this to seconds. What should its orbital radius be? What does this question want me to find? Okay, but here's the key word. Are we in orbit? Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals little m. Which version of AC am I going to use here? Not the v squared over r. 4 pi squared r over t squared. Does little m still cancel? Yeah. Does an r cancel? No, no, no. Because look, Alex, this r squared would move up to here, and I'd have an r cubed. If they're on the same level on opposite sides of the equal sign, they'll cancel out. But no, no, no. An r will not cancel. In fact, what are we trying to get by itself? So I would go cross that out and put a cubed there. How will I move the 4 pi squared over? How will I move the t squared over? So I'm going to get this. R cubed equals big G, big M, t squared over 4 pi squared. How to get rid of a cubed? Holy smokes, Mr. Duke, you mean cube root is actually useful? It's not just something they showed me in my math class? Mr. Duke, do I get to use a brand new button on my calculator today? Yes, you do.
Oh.
Cross out that.
Big
cube root. Now, you're going to have to find where your cube root button is, and we will in a second. But first, let's carefully write out the numbers. So, our orb is going to be the cube root of 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 18,000. Emma, don't forget the. Very good. All over 4 pi squared. I would type that whole thing and then go cube root answer button unless you've got one of the two-level fractions. If you need to find where your cube root button is, I'm going to come around right now and help you. Sorry, I wrote square root. I forgot to put the cube root in there. There's the 3 to remind me that it's cube root. So, R equals 1.48 block. Is the 8 rounded off properly or 1.49? 1.49 times 10 to the what? The 7th? Meters. Okay. And with that, we could calculate how much rocket fuel to get at that high, how much potential energy to get at that high. We could also calculate its orbital speed in a second. What should its altitude be? I'm going to cross that out. But what should its orbital speed be? Okay. That we can do. Are we in orbit?
Yeah.
Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals little m. And I guess now that I want speed, I'll use the v squared over r. Does little m cancel here? In fact, I get v orb equals the square root of big G, big M over R, and you'll use your answer button. Or the other thing you could have done is you could have said, wait a minute, I know the period, they want me to find the speed. Is there an equation for circles that has speed and period in it? Yeah. You could have just gone like this, 2 pi R over the period. I probably would have done that one, because R is sitting on my calculator. So 2 times pi times answer button divided by 18,000. Or that one, this is way more typing. But you'll get the same answer. Have to. What do you get? Calvin, what'd you get?
5,100.
Sounds about right. Anybody else? 5,183?
Yeah.
I know orbital speeds are typically in the thousands. And I know on the Earth is 8,000. So the further out you go, the lower it gets. But I also noticed that this was not as far up as the first example where we got the 3,888. So I figured it's going to be less than that, but more than that, but less than 8,000. I've done enough of these that I can usually get a ballpark rough guess. So what was it?
5,100.
5,100. I'll just go to 3 sig figs. Okay. So our orb equals the cube root of big G, big M, t squared all over 4 pi squared. But it's all cold circular motion. Once you know the law of universal gravitation, then gravity is what's pulling me in a circle. Not all satellites go in circles. Some go in ellipses. Those of you that did calculus with Mr. Camozzi might vaguely remember the equation for the ellipse. So there you would have gravity is pulling me in an ellipse. You'd have slightly different equations, but it's the same kind of a concept. I love watching astronauts on the International Space Station. A few years ago, there was an astronaut from Japan who also played, I think, college baseball, was a very, very good baseball player, so he had some fun.
Space, final frontier.
Bottom of the ninth, the pitcher winds up, and there's the pitch. It's a screaming fastball down the center of the plate.
Its 5-year mission to explore strange new worlds.
The batter eyes the pitch, squints into the sun, digs his feet in, sets his weight, puts the bat on his shoulder, takes a mighty swing, and oh, it's deep. It's going back. Oh, he was robbed. What a catch. Of course you would play baseball with yourself. But one of the first things that NASA discovered about zero G of weightlessness when you're in free fall, everything behaves differently from the way you're expecting. NASA, on their early experiments, wasn't even sure that if you could swallow in space, or would your saliva just pool up and would you drown? We weren't sure. We weren't sure if you could do the bathroom thing in space. I swear to you, there are NASA experiments where astronauts are standing on their heads peeing, and some poor NASA official is taking data. And okay, turns out you can do that upside down, so probably gravity isn't required for that. We weren't sure if you could eat in space. Is gravity required for your throat muscles to get the food? We had many questions. And even today, things behave very, very differently. When Chris Hadfield, Canadian astronaut, was commanding the International Space Station, elementary school students wrote in with experiments that he could try using stuff on the ISS. This one here is great.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use
So what happens if you soak a cloth and wring it out in zero G?
Equipment that was here on board the space station. We may have the coolest wash.
I love that he just casually lets go of the microphone and grabs stuff. He said it took him a day or two. Once he arrived back on Earth, he had to get used to not being able to just leave something in front of him, grab, and so he almost dropped a teacup or a coffee cup, he said, the first day he was back. And he caught himself, oh, can't do that anymore.
Cloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's packed it. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merritt and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth.
This is cool.
Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. it's becoming a
Things
tube.
behave differently in 0G.
The water's all over my hands. In fact, it rings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer in my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet.
So that water then would you saw some droplets fall off. Eventually it will evaporate. And they do have water recyclers on board. The astronauts have a joke. They say today's pee is tomorrow's coffee. It is just how it works. Okay. They filter it through very, very carefully. You saw that surface tension on the hand there. About 4 or 5 years ago, NASA had its closest to a astronaut dying on a spacewalk ever. They were doing a spacewalk, and the astronaut from Italy, what he didn't realize was his water bag had burst, his drink bag. He noticed a bit of water on the back of his neck. Of course, you can't touch that because you're in a spacesuit, so he thought maybe he was sweating, but his partner said, well, maybe your water bag burst, drink it as fast as you can. So he drank some of it. There was actually, I think his cooling bag had also burst. And so the water slowly started to pool and slowly started to go across until it got about this far and it covered his eyes. And NASA practices what's called a blind ingress, when your astronaut partner is disabled and you have to bring your partner in with you. And they executed that because otherwise the water would have shortly covered his mouth and nose and he wouldn't have been able to breathe. So it was actually something as simple as a leaky spacesuit almost cost an astronaut his life. A satellite has an orbital radius of 7.58 times 10 to the 6th meters. What's its orbital speed? What's its orbital period? Let's do A right here. Orbital, gravity is what's pulling me in a circle. B, orbital, gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m. Big G, big M, little m over r squared equals m. For part A, I'll let you write. Sorry, I'm going too fast. Which version of AC will I use for part A? Yep. In fact, you may have already started to recognize, I think we're going to get V orb equals the square root of big G, big M over R orb. Often when we're doing this unit, kids end up memorizing that one on their own just because it's kind of a clean equation. They don't have to, but they do. Which version of speed of AC am I going to use on the right-hand side? I'm not going to do A because we've done a couple of those already, but let's get the T by itself. I don't think we've got the T by itself yet. Where is the T right now? There. Move it to the top. So, Braden, I would do that in my mind. How would I move the big G and the big M over? Yep. Cross those out, put the big G and the big M there. How would I move that r squared on the bottom over? Make that an r cubed. So for what it's worth, orbital period is equal to 4 pi squared r cubed all over big G, big M. How to get rid of a squared? Square root. So Orbital radius is a cube root. You can see the cube. Orbital period is a square root. Okay. So we'll skip A. We've done the orbital speed several times, but let's do the orbital period. It's going to be big square root of 4 pi squared 7.58 times 10 to the 6th cubed. Oh, 6.67 times 10 to the negative 11. Mass of the Earth. No idea what that is. Sorry? No. Yeah. Rocket science is where I reach my limit. I could give you some fairly rough guesses because I know certain numbers. I know that to orbit the Earth right on the Earth's surface is about 5,000 seconds. So this will be a little longer because you're traveling slower and you're doing a bigger circle. So you're probably going to get something in the probably 7,000 range, maybe. But that's a wild guess. Well, the Earth's radius is 6.38 times 10 to the 6th. This is 7.58 times 10 to the 6th. So we're only a little ways above the Earth because we're still in the 10 to the 6th range. So probably in the 6,000s. It's, again, a complete guess. Cole, what'd you get? Sorry? So 6, 5, 6, I'll just go to 3 sig figs. You can also see we're doing some pretty heavy-duty calculator work. It was this unit here. This is why I yelled at all of you last year about getting a good calculator. Because can you imagine trying to do this on one of those calculators that doesn't let you backspace or edit or... It's doable. Had a couple of kids do it. Typo? Mistake? Yeah. Is Cole right? Maybe Cole's wrong. Okay. Yeah. So what was that? Oh, that should be a 24. You know what? Cole is right. I wrote down the wrong number. It's 24 down here, which would have given all of you the wrong number. Sorry. Thank you. This is why I have the formula sheet. I shouldn't be going from memory, and I never bother memorizing these because they're on the formula sheet. Okay? So, Elias, here's your answer. Okay? You can write this down if you want or not. This is purely nerd trivia. Elias, Isaac Newton came up with this equation. But big G, was so small, he didn't know how to calculate it. He did not have the 6.67 times 10 to the negative 11. So what he did is he set everything up so that big G's would cancel. That was his workaround, which limited him because there's certain things he just couldn't solve. About 100 years after Isaac Newton, a scientist named Cavendish came up with a very, very clever experiment to measure big G. How the heck do you measure something so small? 0.0000000000667. He did this. Okay. This is a recreation of the famous Cavendish experiment. So he put some weights on the end of a beam suspended from strings. You can't see the fishing line, but there is fishing line. This isn't a very high resolution video. I need to try and find a better one. He did this in a very isolated room. No magnets, mirrors. No other strings, I think he means to say. No tricks. So remember, any two masses will exert a force of gravity on each other. So this bar can rotate very easily. What Cavendish then did is he put a really big mass right there and a really big mass right there, and that caused the bar to ever so slightly rotate. And that caused the rope to twist. And he knew how to calculate the force of the twist. What's causing the twist? Gravity is what's causing the rope twist. And he was able to get big G by itself. So watch. We've put two lead bricks with a heavy mass there. And if you wait for it, he left it alone in an enclosed room for months. But can you see it? And he didn't have this ability to see, high-speed video or anything like that. But it is rotating. It is exerting a force, and he was able to measure that twisty force, which must be the same size as gravity. You can reverse it. Really, he did this in the 1680s. Really clever technology for what he was doing at that time. Like, this was a nice, aha, way to go moment. So Elias Cavendish did the experiment, repeated it, and he came up with and the first thing he did was this. Gravity equals gravity. Big G, big M, little m over r squared equals mg. $9.8. 6. He just found that. We've known the radius of the Earth actually for well over 1,000 years. A Greek mathematician in 300 BC cleverly calculated the radius of the Earth by comparing shadows in different locations. He got the m by itself. This was the first time we had calculated the mass of the Earth. He said, m is going to be our old friend Gur, Gur with a squared there, all over big G. And when he crunched the numbers, he got 24th. I keep doing the 28th, sorry. And when he crunched that, he went, oh my goodness. That there was way too big from the previous estimates. Now, the previous estimates, all they had done was taken shovelfuls of rock and dirt, weighed those, get an average shovelful, and then estimate how many shovelfuls made up the volume of the Earth. And their estimate, it turned out, was way too small. Earth has a much larger mass. This was the first indication right there that it isn't rocks all the way down. What do we now believe is at the center of our Earth's core? An iron, iron is denser than rock, an iron core. This was the first, hey, it's not rock all the way down there. This was a very momentous occasion. By the way, his value for G was a little bit off, and so his value was a little bit off. We've refined this as our experiments have gotten better, but you asked, how the heck did we get the mass of the Earth? There was the first calculation right there. Okay? Yep.